I'm Theo. Theodora is my full name, Economou. And I have a PhD in statistics, but I apply that to climate, and I'm a postdoctoral fellow at the University of Exeter. And that's my main job, other than being a poster boy. Or so today I'd like to talk to you about storms a bit. So here's a plot, but before I go into that, I'd like to throw a name at you, Xynthia, windstorm Xynthia. I'd like to see a show of hands of how many people actually know this windstorm. So good, so a big number of you. So Xynthia was a storm that hit Europe a few years ago and caused a lot of damage. So it's already something scary, but I'd like to put another question to you is, well, what if we could get a windstorm Xynthia that has the strength of windstorm Katrina or windstorm Andrew or Sandy, right? Because as we know, the European storms are usually, they're always weaker than the hurricanes, right? But what if we could get one at that strength, right? That would be devastating. So we would get things like this, images like that, houses dropping down in Europe. Yeah? So that's pretty scary. And that's one of the questions we'll try to tackle in this project I work on that is being provided by the AXA Research Fund. And in short, here's another plot. I like these plots because I'm a statistician. I like to plot densities, I guess. But this, I'd like to illustrate how we should try to tackle or answer that question. This is a plot, a sort of imaginary plot of storm intensity, right? So think of the x-axis as a measure of how strong a storm is. And this, on the y-axis, is some kind of measure of probability or how, let's say, how likely that intensity is. So a given storm would have an intensity distribution that looks like this, right? Any given storm can have this distribution. Many of them will be somewhere here, so that means that they don't have much big intensity, so smallish intensity, and they're more likely. However, all they can do is sort of cause a bit of rain, a bit of wind, break your umbrella like this guy here. But then what about down here? Right? These are the strong beasts, right? So these are the ones that might cause this. So what do? Well, we apply some models basically to, let's say, emulate this kind of distributions, to fit these kind of distributions to observations, storms that have occurred in the past, over the last 30 years. And because these are quite complicated things, storms, you see, this is a big one over Europe. This is, I don't know if you can see, this is Italy here, Sardinia. And they hit Europe, so they're quite, they're varying in space and time and all that. So basically we take this distribution and we make it different for each location in space, for each point in time, for each season, for each month. We also include things in there like climatic variables, so variables that that capture climate variability. And in that sense, they also capture climate change if it's in there. And we also include those in the models in order to fit this distribution. And then once we get a model for this, then we follow the tails go along the tails, and we ask ourselves, what's the limit, how far out that tail would go, which would answer our question, how intense could they get over Europe, based on that 30 years of information. And once we do this, we have, we can predict, we can simulate potential storms and then see how they behave. But before I talk about the results, I would like to give to you another aspect of what we're asking ourselves, which is mind the gap between the storms. This is a very sort of British phrase. If you've ever been to the subway in London, mind the gap, don't fall in the lines of the subway. But in this case, I'm referring to the gap between the times of occurrence of storms. So suppose you're standing somewhere in space and the storm's coming through, so you're standing in the middle of Paris like we do, and there's storms coming through every winter, and you think of them as occurrences in time. So are these occurrences clustered? And if it helps, you can think of them as buses, right? So you're standing in the bus stop. What are you waiting for? Well, you're waiting for the bus. Nothing arrives for a bit. Then instead of the one bus you're waiting for, you have 3 buses of the same number arriving at the same time. Yeah? They arrive in a cluster. Now, why do they do that? Well, they've been in traffic. Yeah? Traffic, there's something happening in traffic, which is a complex system, that caused them to cluster. Right? So in that sense, traffic would be your climate or your atmosphere, right? And the buses would be your storms. Right? So do they cluster? So and in each one of them is how extreme would it be, right? So are they extreme and do they cluster? And why is that important? Well, because you don't really want to be hit by 3 consecutive storms that are also strong, right? So the other question would be, if they cluster, does that mean they're also necessarily intense, right? So is there a relationship between this clustering and how strong they would be? Because the worst case would be, yes, they cluster, and yes, they can all be very strong. And we apply some kind of other kind of statistical model to answer these questions, and the answers to them are basically, yes, they do cluster, and yes, we do find evidence that they can cluster and be extreme at the same time, right? Which is not what you want. And in fact, the answer to the question whether windstorms in Europe could be as strong as hurricanes in America, that's also yes. We're finding that in certain locations, for example, over Iceland or over Norway, Scandinavia, they can. Although the uncertainty of that is quite big, but still, we're finding evidence of that. So I guess the takeaway message is, well, brace yourselves, yeah? We could get a hurricane, we could get them clustered. So society, I guess, insurance companies or reinsurance companies like AXA could keep this in mind and try and be prepared for it. And thanks for your attention.